Hello, everybody. Today, we're going to talk about a few new chemistry concepts. Specifically, we're going to go over limiting reactants, excess reactants, and three different ways to think about yield. We'll talk about theoretical yield, actual yield, and percent yield, which is a way of comparing the other two. If that doesn't make sense right now, that's okay. That's why we're going to talk about it. One other thing I'll say before I jump into instruction is that this is often considered by many chemistry students to be the most challenging and most confusing thing that we do in chemistry. And I'm not saying that to scare you away. I'm saying that to make sure that you are prepared for this to potentially be a little bit confusing, and also to make sure that you are not too hard on yourselves if this doesn't make a ton of sense right away. Now, I have tried to make this as streamlined and as simplified as I can, but just know that this is something that many students struggle with, and it's okay if you struggle with this as well. So let's get into it. First of all, I have a crisis that I need solved right now. I am making cheeseburgers for a barbecue. I'm not inviting anybody to the barbecue though, because, pandemic and all that. But I'm making cheeseburgers for a barbecue and I'm running low on ingredients and I need to know how many cheeseburgers I can make. So each cheeseburger, the recipe for a cheeseburger is you need a bun, you need a patty, and a slice of cheese. And I have 4 buns, 3 patties, and 5 slices of cheese. So my question is, how many cheeseburgers can I make? Do you have an answer? I can make 3 burgers. Now, I have some extra stuff, but I can only make 3 cheeseburgers because I only have 3 beef patties. Or maybe these are impossible patties, or maybe these are mung bean patties or something. I don't know. I don't know. But we can only make 3 burgers because we are limited by that number of patties. So we'll have a bun and we'll have a couple slices of cheese left over, but we can only make 3 burgers. Now, there's a reason that I'm talking about this, which is that this directly relates to a concept in chemistry. So let's try and think about this same situation, but in the framework of a chemical equation. So if this was a chemical reaction, we would say that the balanced equation for making a cheeseburger is 1 bun and 1 patty and 1 slice of cheese makes 1 burger. So the bun, the patty, and the slice of cheese are the reactants, and the burger is the products. So the reactants that I have here are I have 4 buns, 3 patties, and 5 slices of cheese. So another way that we could say that I can make 3 burgers is say that I can make 3 products. I can produce 3 burgers. And I'm gonna have some reactants left over, the bun and 2 slices of cheese. So the number of patties that we were dealing with, that is the thing that limited how many burgers we could make. And then the buns and the cheese were in excess, which gets us to our first set of concepts, chemistry concepts, limiting reactants and excess reactants. Because in a chemical reaction, the same exact thing happens. When you perform a chemical reaction on a lab bench, in a lab, or when you're doing research or for any other reason, it is very, very unlikely that you're going to have a perfect ratio of reactants where they will all react together and everything will be converted to a product and there will be nothing left over from the reactants. Usually, you've got a little bit more of one of the reactants than the other reactants. And so, in most cases, we end up with limiting and excess reactants. The limiting reactants being the reactant that runs out first and limits how much product it can form, how much product can be formed. That's why it's called the limiting reactant, is because it limits how much product can be formed. The excess reactant is any reactant that doesn't get used up in the reaction and that there's going to be some left over of. So the limiting reactant in that barbecue crisis was the patties because we only had 3 of those, and that limited how many burgers we could ultimately make. So that was the limiting reactant. And then the excess reactants were the other 2, the bun and the cheese, which we had some left over. Now, we're going to stop talking about barbecue and we're going to start talking about chemistry here. And one really important note is that going forward, and whenever you are dealing with any calculation that we need to do in chemistry, including these, you have to be working with balanced equations. It simply does not work if your equation is not balanced because your mole ratios have to be correct. So, anytime you're looking at a reaction, just take a few seconds to double check that it is balanced. And if it's not, balance it yourself. So, let's take on a practice problem here, a chemistry practice problem. Let's try to apply those concepts of limiting and excess reactants to this new scenario. So let's say that we want to make magnesium oxide using this reaction. Magnesium and oxygen reacting together to make magnesium oxide. Now, what I just say, the first thing you should do is check to make sure that this is balanced. So I'm looking at this and I'm seeing two magnesiums in the reactants and two magnesiums in the products. So magnesium is balanced. I'm seeing two oxygens in the reactants and two oxygens in the products. So it looks like this is a balanced equation and we don't have to worry about that right now. We can move forward. Now we have 6 moles of magnesium and 4 moles of oxygen. Those are the actual reactants that we are going to put together and react to try to make magnesium oxide. So my question is, how much magnesium oxide can we actually make? How many moles? And which one of the reactants is going to be limiting and which one is going to be excess? So if you feel like you have an idea of how to do this, go ahead and pause this video right now. I'll stop for a couple of seconds and give you a chance to try and solve this on your own. All right. Now let's do it together. I'm going to switch over to my document camera. Nice. All right, that looks good. So we are dealing with 6 moles of magnesium and 4 moles of O2. And we want to know which one is limiting and which one is excess and how many moles of magnesium oxide we can actually form. So what you really need to do here is you need to convert both of these. You need to take a trip through Chemistry County or do some stoichiometry or however you want to say it, and you're going to figure out how many moles of magnesium oxide can you make with each of these different ingredients. So if we have 6 moles of magnesium oxide, the molar ratio between magnesium and magnesium oxide, sorry, we have 6 moles of magnesium, and we want to know how many moles of magnesium oxide we can make. The molar ratio between magnesium and magnesium oxide is 2 to 2. This comes from the balanced equation. 2 moles of magnesium can make 2 moles of magnesium oxide, which means that we have enough magnesium here. If we take 6 times 2 and then divide by 2, we have enough magnesium to make 6 moles of magnesium oxide. Now we have 4 moles of O2, and the molar ratio between O2 and magnesium oxide is a 1 to 2 ratio. For every 1 mole of O2, we can make 2 moles of magnesium oxide. So if we solve that, 4 times 2 is 8. So we have enough oxygen to make 8 moles of magnesium oxide. What's it going to be? Are we going to make 6 moles of magnesium oxide or 8 moles of magnesium oxide? Well, we're only going to be able to make 6 moles of magnesium oxide because what's going to happen is that we're going to put these two things together. They're going to react until all 6 moles of magnesium oxide have been used. And at that point, we will have made 6 moles of magnesium oxide. Did I say magnesium oxide again? 6 moles of magnesium have been used. And at that point, we will have made 6 moles of magnesium oxide. And we're going to have some oxygen left over because we have enough oxygen to make 8 moles of magnesium oxide, but we're only going to make 6. So basically, let me switch colors here. Magnesium is going to be our limiting reactant. Oxygen is going to be our excess reactant. And this number over here is something we haven't talked about. This is going to be, I'm foreshadowing a little bit, that's going to be something we call our theoretical yield, the amount of product we expect to make. So I hope that that makes sense. Now, I foreshadowed this about 2 seconds before I actually was going to talk about it. That number, that 6 moles of magnesium oxide, that is something we call our theoretical yield, because based on our calculations, that's how much magnesium oxide we would expect to produce from this reaction between 6 moles of magnesium and 4 moles of O2. And so theoretical yield is the amount of product expected from a reaction, which is determined by the limiting reactant. Again, it's called the limiting reactant because it limits how much product can be formed. So the amount of product that you can expect to be formed based on that limiting reactant is your theoretical yield. Okay, now let's make this real here. Let's combine some of your stoichiometry and dimensional analysis skills into this concept of limiting and excess reactants and theoretical yield. So we're working with the same chemical reaction here, magnesium and oxygen reacting to produce magnesium oxide. And we have 48.6 grams of magnesium and 64.0 grams of O2. So we've got masses here. What will be our limiting reactant, excess reactant, and theoretical yield of magnesium oxide in grams in this situation? This is tricky, but I want you to pause the video, give it a try, and come back when you've given it a try, and I'll walk you through how to do it. All right? And I will leave you with this picture of this puppy reminding you that you can do this. Did you pause the video and give this a try? I hope you did. Because now I'm going to spoil the whole thing and I'm going to tell you how to do it. Let's switch over to the document camera again. Okay. Now this is a little bit tricky, folks. I'm just going to warn you in advance. We're going to set it up the same way, but it's not going to be a simple one-step calculation this time because we don't have mole values. We want to figure out we want to figure this out using gram values. And in fact, we're being asked to calculate the theoretical yield in grams, not in moles. So this is actually going to be quite a bit more complicated than what we did before. But let's just start with magnesium. If we have 48.6 grams of magnesium, and we want to know how many grams of magnesium oxide can be produced, we're going to have to go through several steps here. We're first going to have to convert moles of magnesium, sorry, grams of magnesium to moles of magnesium using magnesium's molar mass, which is 24.31. Then we're going to have to use a mole ratio, aka a magic box, to convert from magnesium to magnesium oxide. Now, we already know this from this question up here. For every 2 moles of magnesium, we can produce 2 moles of magnesium oxide because there's a 2 coefficient in front of both magnesium and magnesium oxide in the balanced equation. Now, we're still not done because if we were to stop there, we'd have how many moles of magnesium oxide we can produce. And we want to know grams. So we now have to use the molar mass of magnesium oxide, which is 40.31, to figure out how many grams of magnesium oxide we can make. Now punch that into your calculator. It'll be 48.6 times 1 times 2 times 40.31, all divided by 24.31 times 2 times 1. And you should get 80.6 grams of magnesium oxide. So you have enough magnesium to make 80.6 grams of magnesium oxide. Cool deal. Now, what about the oxygen? We're going to do the exact same thing for oxygen. If we have 64 grams of O2, we need to convert that all the way. We need to go to grams of magnesium oxide. So we're first going to use the molar mass of O2, which is 32.00 grams, to convert from grams to moles, or in other words, to go from the Grand Canyon to the Molar Mountains. If you watch that video on Chemistry County, you know what I'm talking about. And then we're going to use the magic box, aka the mole ratio, which is, again, we know it from this previous one. For every 1 mole of O2, we can make 2 moles of magnesium oxide. And then we're going to use this exact same conversion factor right here to convert from moles of magnesium oxide to grams of magnesium oxide. Plug that all into your calculator, and you should get 161 grams of magnesium oxide. So you have enough oxygen here to make 161 grams of magnesium oxide. So I hope that that answers your question. Because if we have enough magnesium to make 80.6 grams of magnesium oxide and enough oxygen to make 161 grams of magnesium oxide, that means that the magnesium is going to run out first. It's going to be our limiting reactant. All of this magnesium is going to react away. We're going to end up getting 80.6 grams of magnesium oxide, and the oxygen is our excess reactant. There's going to be a bunch of oxygen left over because you've got enough of it to make 161 grams of magnesium oxide, but we're only going to make 80.6. So hopefully that's what you got in your calculations as well. Now, I know that that is a doozy. I know that one was not easy. And in fact, that may have confused many of you, but there will be some practice that you can work on here. We are always available for your questions. So if you get confused, please make sure that to know that you are, number one, not alone, and number two, not without support. We are here to help you out. Now, we've already covered one type of yield. We've talked about theoretical yield. It's how much product do you expect to get from a chemical reaction, and it's based on the limiting reactant. Now, here's the thing. In the real world, things aren't perfect. Theoretical yield is what you would expect to get if everything was exactly perfect, meaning that all of your reactants were pure, there was no impurities anywhere, everything was fresh and new, and nothing had degraded or gotten old or wasn't working anymore. And in reality, that's not the case, right? There is a high likelihood that when you do a chemical reaction, one of your reactants might have a slight impurity, or maybe it's old and it's just kind of been, degraded a little bit or something like that. So when you actually do a chemical reaction, oftentimes your yield is different than what you expected. In other words, your actual yield, the amount of product that you got in a reaction, often differs from your theoretical yield. So we have a different word for it. We use actual yield. And theoretical yield and actual yield are generally two different things. Oftentimes, the measurement of how well a reaction went, or sometimes how good a scientist you are, depending on whether, you know, your actual yield has anything to do with your skill or your knowledge. But oftentimes, percent yield is used to basically measure the success of a chemical reaction. Like, how close was your actual yield to your theoretical yield? So it's literally just the percent of the theoretical yield that you actually obtained. So if you ever needed to calculate percent yield, you would do it using this equation: actual yield divided by theoretical yield times 100. It's very simple. Sometimes people say percent yield is equal to what you got divided by what you should have got times 100. That works too. So this is also something that you will need to know how to do. Let's give it a shot. Going back to our practice problem, that same chemical reaction with magnesium and oxygen reacting to make magnesium oxide, we calculated that our theoretical yield was 80.59 grams, or we actually said, because of significant figures, 80.6 grams of magnesium oxide. So let's say that in reality, we mixed that we mixed those two reactants together, the 48.6 grams of magnesium and the 64.0 grams of O2, and our actual yield was 77.34 grams. That is the actual amount of magnesium oxide that we got. So what was our percent yield? Give it a second. Try this on your own and come back in a few minutes. Press pause and come back in a few seconds, and I'll tell you how to do it. All right. Well, the good news is that this is quite a bit simpler than this whole process. We know that our actual yield was 77.34 grams. We know that our theoretical yield was 80.6, and I'm going to use 80.6 because it's actually what we got with correct significant figures. So our theoretical yield was 80.6. 77.34 divided by 80.6 times 100 should give us 95.97, or since we're dealing with three significant figures, we'll say 96.0%. That's our percent yield. And that brings us to the conclusion of this video lecture. So, again, if something in there didn't make immediate sense to you, don't freak out. That's okay. And you are not alone. That is how it goes for most people. In that case, you just need to make sure to come to our office hours. You need to make sure to ask us questions, shoot us emails, whatever you need to make sure that this ends up making sense for you. And of course, don't be hard on yourself. So keep in touch. Thanks for watching, and I'll see you next time.